Well, hello and welcome YouTube to Mr. Robinson's Q&A Power Hour, straight out of the shower, where I am going to take my students' questions that they asked on right triangles and trigonometry, something where we've concluded this unit. If you've been following my video series, The Big Ideas Math, Integrated Math 2 textbook, this would be stuff from Chapter 9. So I'm going to take their questions and I'm going to attempt to answer them the best that I can. 19 questions were asked, and at a time I was thinking of taking and consolidating them into like 10 questions as a whole, just like a lump sum of like whatever they were asking, ask ChatGPT to do it and make 10 questions out of it. But 19 isn't very many in comparison to what it could be. So I'll try and keep it within an hour as well. I haven't really read the questions. I imagine a lot of them are going to be asking trig related things because that was the last 3 sections of that particular chapter. But if you want to know what else there was Pythagorean theorem, special right triangles, the 36, 90, 45, 45, 90 triangles, and right triangle similarity, where you have an altitude drawn in a right triangle, and then boom, 3 similar right triangles are made. I don't know what kinds of questions they're going to ask with that. If they do, I kind of hope that they ask some and they found a way to ask them so I can answer them for them. Anyway, check the description section down below if you want to find timestamps to each question that is asked, so you figure out what kind of question you'd want to get answered. There may be repetition in questions, and if there are, I'll just say I answered that before, kind of, or I answered something similar. Go find the one above, just to kind of save time and to not be repetitive. But let's go ahead and see what they came to ask me in this set here. Okay, so here we go. The first question asked, let me dim my screen a little bit, is how do you know when to use the negative form of cosine, sine, and tangent? So what I believe they're actually asking is about inverse sine, inverse cosine, and inverse tangent, because it has that negative appearance in them. They're talking, I believe, that because I can't think of anything else that they'd be asking about, but this, where there's a negative right there, sine to the negative first power, right? Something like that. Let's just say of x, just for now. This kind of appearance, okay? So this one, or cosine or tangent. How do you know when to use it? Well, there are kind of 2 answers to it. Number one, well, they're both the same answer, but we use it to get the angle measure of a value. This x right here is a ratio of the opposite over hypotenuse, whatever it is in your triangle. The result is some theta that is an angle measure. We use it to get that angle measure. Now, when you say, how do you know when to use it? You use it when you need to find an angle measure given a ratio. But in your particular case, you will know also when to use it because you will have something that's set up as, say, the sine of an angle, and it equals a ratio. And then, let me get that spaced out a little bit more. And then your next step is, I need to solve for that theta. I need to get this theta by itself, because you'll have a ratio, right? You'll have some number here. You're not solving for a number. The number's already solved for. But this is a variable still, and you got to find that. Well, the way to get this by itself is to get rid of sine, and the way to get sine by itself is by using inverse sine of this side, and therefore you have to use it on this side here. The inverse sine of the sine of something is what cancels it out. And I've tried to stress very heavily in my class, probably in videos as well, in that, you know, some people suggest, oh, divide both sides by sine, which means very little because, number one, we're not multiplying by anything. Number two, sine's not a number, it's a function, and, you know, all those things involved. But this particular function has an inverse called inverse sine, and that's what it looks like. So how do you know when to use the negative form of cosine, sine, and tangent? I'd use sine very specifically here, but it doesn't matter. It can be interchangeable. If this says tangent, use inverse tangent, things like that. You do it to find an angle measure. And, you know, therefore now theta is now the inverse sine of something. Of that thing, right? And I wrote that up here as well. To give one quick example of that, we have some theta right here, and this length is 4, and this length is 8. Actually, I don't want to use something that I know the answer to. This one's 5, and this one's 8, right? So we can say, all right, I'm going to set up an equation that says the sine of my angle equals opposite over hypotenuse, 5 over 8. Now I take the inverse sine of both sides, which cancels out the sine on the left side and gets theta all by itself. And then you now have the inverse sine on this side. And the inverse sine of 5/8 is some number. Actually, maybe I should have used the 4/8 because I'd know what that number would be. It would be 30 degrees. Why don't you try that if you want to? So let me bring the 4 back. This is clearly unplanned. Yeah, if you had a 4 right here, 4 over 8, I happen to know that this one will be exactly 30. You can use your calculator and check that one out. But yeah, you use it to find an angle measure, right? That's the point. It's not the negative form, and I think that's the other thing I want to address. It's not the negative form of it. It's the inverse of them. You use it to invert what you have. It's like saying, how do you know when to use division? Well, it's the inverse of multiplication. So you use it when your variable is being multiplied by something that you want to get rid of. Stuff like that. All right, there's that question. Hopefully that is answered well. Let's go to the next one that asks, how do you multiply square roots when finding missing side lengths of a triangle? Let me start up a new thing here. Square roots meaning, so I think we're talking about the special right triangles. So let me get an actual right triangle here drawn. So like in a 45, 45, 90 case, you know, here, their ratio relationship is 1 to 1 to root 2. So that means that whatever this length is right here, let's say it was 2 root 10, that I wanted to find out what this x was right here. So this x is going to be root 2 times larger than whatever this guy is. So x is 2 root 10 times root 2. Now the question asks is, how do you multiply square roots when finding missing side lengths? I mean, this isn't new for us. The 45, 45, 90 is, but not this actual simplifying radicals concept. Square roots multiply with square roots. The idea of the property is, and this works both ways, this also works to simplify radicals, which we'll get into on this very problem, that you can merge these two under the same square, what I call square root hat. Or if they were cube roots, then they can go under the same cube root hat together, things like that. This is a property that's true for multiplication and division of radicals, of irrational values. The root 10 times root 2 can multiply together, and you'll get root 20, as an example. Now, that is how you multiply them. So you only multiply them together if they are square roots together. I hope that makes sense. And then if there was like a times 3 right here, then it would be 6 root 20. Whatever like that. Only the rationals multiply with rationals, irrationals with irrationals, things like that. Now, this would still have to simplify as a radical because it contains a perfect square factor, which brings me to my next point, that this works this way as well. 20 is a product of two numbers, not just 2 and 10, but also 4 and 5. And I bring up 4 and 5 because 4 is a perfect square, and that I can get it in its own square root. Own square root. 5 gets in its own square root, and I can therefore take the square root of 4 and get 2, and this 2 multiplies by this 2, and you get 4 root 5. Obviously, I'm going longer in the problem than perhaps need be, but that is the idea, that you can multiply things together, fuse the square roots together to become a single square root of something, and likewise, when you simplify a radical, you factor out any perfect squares because they can go in their own separate square roots as a product. In the same way. This is interchangeable, goes both ways. We've been using this since chapter, I think, 4. If you've been in the integrated math 2 set. And I'm not saying you can't ask the question. I'm just saying that it's not new for that. All we now have to know is what our 30, 60, 90 ratio relationship is, what our 45, 45, 90 ratio relationship is. Now, you didn't ask about dividing. And I'm not going to answer it in detail unless I see the question, but it has to do with rationalizing the denominator. Yes, they can divide, but if you ultimately have a square root still on the bottom, you got to take care of it in some way. So we'll see if a question's asked about it, or ask me in class. All right, next question is, what are the ratios of the sides of a 30, 60, 90? So I guess that this carries on. So far, I mean, 2 of the 3 questions haven't been asked about trig, so I didn't know to expect that. So the 30, 60, 90 triangle, I just mentioned in the last one, the 45, 45, 90 triangle is 1 to 1 to root 2. Now, my students should have taken notes on this kind of stuff. They can obviously look it up at any time. I'm fine answering it, though, but I just want to mention how you can remember this in some sort of way. First of all, the 45, 45, 90 has the 1 to 1 to root 2 ratio relationship. We know that 1 plus 1 is 2. I'm not saying that is something you'll mathematically have to deal with in this. I'm just saying that's a way to remember those numbers, I guess. Also, Pythagorean theorem, 1 squared plus 1 squared is root 2 squared. The 30, 60, 90 is 1 to 2 to root 3. It's 1 to 2 to root 3, but you got to be careful as far as where they go. Opposite, the smallest angle should be the shortest side. 1 is smaller than either 2 with the square root of 3, so this will be a 1 right here. Now, that doesn't mean the number's 1. It means whatever this number is, we can multiply this by a certain amount to get this and this. Now, what number's bigger, 2 or the square root of 3? Well, 2 is the square root of 4, and opposite the largest angle should be the longest side. So root 4 or 2 should go here. And the root 3 should go here opposite the 60. What this means to us is the short leg of the 1, I can find the long leg by multiplying by square root of 3, or I can find the hypotenuse by multiplying by 2, and likewise I could get to the short leg by dividing by 2 or dividing by root 3 from these places. And I'd want to go from the long leg to the hypotenuse by going to the short leg first. So if you see it in my examples, you'll know exactly what I mean. But those are the ratios. I won't dive into a proof right here, but it has to do with equilateral triangles if you want to. I think I have a lecture video somewhere that dives into the proof stuff. So if you go to the 9.2 portion, find my lecture video, find the 30, 60, 90 triangle, you will see my proof on that exact thing. But I hope that answers your question. Thank you for asking that. Next question is, or statement, I'm having trouble with the sine, cosine, and tangent and which ones they are and when to use them. There could be a bigger talk to be had. I'll try and condense it into something significantly smaller. Sine, cosine, and tangent are each, there's no one that's better than the other. Like, to just really hit home, no one's better than the other. No one's like, well, I really prefer this one. No, it's nothing like that. Everything's completely dependent on the angle to which you're referencing. Let's say it's this guy right here. And which side lengths are known / labeled / you have to find, right? If there's some sort of, X, Y, Z right here, but X is the one that you need, and Z is the value that you have. In relation to theta, the side opposite is X, and the hypotenuse is Z, and therefore I will use sine because that function is specifically designed to understand that the opposite of hypotenuse ratio is what gets you this angle, the sine of the angle measure, because we remember that from SOHCAHTOA. So I'm having trouble with sine, cosine, tangent, which ones they are and when to use them. Remember how to spell SOHCAHTOA. That will get you a good head start. Sine uses opposite and hypotenuse. Now again, there's no one that's better than the other or anything like that. Your calculator, as much as we're going to use it, your calculator is very aware that when you hit sine of an angle, it's dividing whatever that right triangle's opposite divided by its hypotenuse would be, because every right triangle with this angle measure is similar to one another, that this divided by this will always be constant. Remember when I said that if this was 4 and this was 8, if you heard earlier, this would give you 30 degrees. It will always give you 30 degrees, or whatever. The sine of 30 is always 0.5, because whatever this is always twice that amount, like a 30, 60, 90 triangle would. But that's what sine would always use. Now cosine would use adjacent over hypotenuse. So the adjacent leg to theta is the y variable in this case. This would be adjacent. And let's say you had that, or you were trying to find it, or you had the hypotenuse, you're trying to find the hypotenuse, something like that, or you're trying to find the angle with these things labeled. Basically, if these were your 3 labels, you'd be using cosine, because relative to this angle, this is the adjacent leg, this is hypotenuse. Your calculator is very aware that those are the 2 things that divide when you use the function cosine. Tangent is opposite over adjacent. Whoopsie, I totally lost my stuff. There we go. Tangent's opposite over adjacent, where ADJ, opposite this angle is X, the adjacent is Y. It would divide those 2. Get that ratio for you as far as what you need to solve for something. So I'm doing this very generically. I'm not using actual examples with this stuff outside of showing you where they are, but there's that. Now, the other thing to keep in mind is everything is relative to the angle you're using. So this theta, if it was over here, this is no longer opposite. This is opposite is now on this side, like the y. The adjacent is now the x. Hypotenuse is still the hypotenuse. That won't change. But as far as opposite over adjacent or whatever goes, theta now being here means we're going to use those. And don't worry about the right angle one. We're always referring to the acute angles when we talk about it. There's a way to get sine, cosine, and tangent of 90, and your calculator will show you what they are. But you're not really talking about right triangles anymore. You're talking about unit circles, which means you're talking about IM3 or pre-calc. Only worry about the acute angles. Okay, hopefully that answers your question there. Thank you for asking. Next question. So yeah, I expect a lot of trig, but here we go. When using sine, cosine, sine, and tangent, at what point do I use the negative version of them? So I don't know if it was the same person asking with the first question up above. I'll just go ahead and mention I answered it up here. The one that I'll answer it very shortly here in two ways. Number one, there's no such thing. When you're saying negative version, you mean inverse sine, cosine, tangent. Second thing is you use it to find angle measures. You use it on ratios to find angle measures. But I answered it in detail up here. Okay. All right, next question asks, where am I? I still don't fully understand the 45, 45, 90, and 30, probably 30, 60, 90 triangles. How can I remember what to multiply to get whatever side is missing from the triangle? I'd say I'm not big on memorization. I'd say at some point you kind of familiarize yourself with them. I'll say them again. I mean, I'll say them over and over, right? That's a familiarity thing. The 45, 45, 90 one's a lot easier to come up with on your own. The ratio is 1 to 1 to root 2. We know that 1 is smaller than root 2. The reason why this one's easier to kind of come up with on your own is a 45, 45, 90 triangle is an isosceles triangle. If these two angle measures are the same, then their sides opposite them are the same. They have a 1-to-1 ratio relationship. 1-to-1 isn't something that you heard for the first time in this chapter of this math class. Hearing something as 1-to-1 means it is exactly pairing equal to it. These are exactly the same length. I think we can all come up with that pretty straightforward. And when I did a proof in my own math class for this in the lecture stuff, which is also in that same lecture video I talked about, find my 9.2, the lecture video in my 9.2 thing if you're in my Google Classroom. Or it's titled, there's a YouTube video I have. I should probably link it down below. I should probably link my Pythagorean theorem stuff, right triangle stuff, and special right triangles and trig stuff. Anyway, I can use Pythagorean theorem to find out what this length is right here. If I don't remember that it's root 2, let's just do 1 squared plus 1 squared and figure that out. 1 squared is 1. And take the square root of both sides, you get the square root of 2. I mean, it's a very fast, thing to get to. I mean, 1 plus 1 is 2. Obviously, it's a root 2, but 1 plus 1 is 2 is a nice way to remember that as well, just saying it out loud. It rolls off the tongue very well to hear 1 to 1 to root 2, 1, 1, and 2 there. Likewise, and I already talked about 30, 60, 90 triangle a little bit here. Someone asked about the ratios of the sides. Let me, before I talk about it, you said what to multiply to get whatever's missing. Hopefully you recognize this means that from a leg you find the hypotenuse by multiplying by root 2, and you go from the hypotenuse to a leg by dividing by the square root of 2. The whole 1 to root 2 ratio relationship means exactly that it's root 2 times larger than the leg. So you either multiply it by it or divide by it. The 30, 60, 90, and I've already brought it up in the other question, so maybe I'll go quicker here, but its ratio relationship is 1 to 2 to root 3, being very careful of the fact that 2 is bigger than root 3. Therefore, 2 has to do with going opposite the 90-degree angle. But it's better to say 1 to 2 to root 3 than it is to say 1 to root 3 to 2. You can tell it doesn't roll off the tongue as well because we count 1, 2, 3. We don't count 1, 3, 2. And that root being the last number kind of is nice as well. I think those are things that we can just plant in, right? 1 plus 1 is 2, and count 1, 2, and 3, and each of them have a little square root at the end of it. There are little things to place, and honestly, there aren't too many things to memorize here, right? There's a squared plus b squared is c squared. There are these two sets of special right triangles, and there's SOHCAHTOA. And that's it. And I think we all know a squared plus b squared equals c squared, just from IM2 or from just alphabet-based things. We've done them before. SOHCAHTOA is a single spelling, and from that, everything will be generated. The other thing I'll mention, when you get a quiz or a test, just draw these on immediately. Keep it in mind right before the test and do that. The question is, do you know how to compute with them afterward? Anyway, opposite the 30 is 1, opposite the 90 is 2, and opposite the 60 is the root 3. So from 1 to root 3, you multiply by root 3. Here you divide by root 3. Here you multiply by 2. Here you divide by 2. And I always go from either of those to the short leg. And I did talk about those a little bit more up above. Maybe it'll be repetitive now if you go back and listen to it. But hopefully, I don't know if that answers your question, but that's I hope I addressed it. I don't know. All right, the next question is: will you tell us when to simplify, or will we need to determine when to simplify in the test? I mean, if I don't mention it on a question, you can ask me. The test is already written. I didn't write it, so I can either add those instructions on, or you can just ask me. For the most part, it's one of those things where if it's a special right triangle, you're simplifying. If it's something from like 9-1, 9-2, 9-3, you're simplifying. If it's 9-4, 9-5, 9-6 on trig, you're probably doing a rounding to the nearest tenth or nearest whole number or whatever it is. Because, yeah, I think that's pretty much it. You know, when we're taking the square root of something, it's like, okay, if you're taking the square root of something and you can simplify it, you do that. The exception is maybe a word problem. If you get the square root of 20, 2 root 5 is an exact answer, but if we're talking about how many feet is the ladder, you know, how long is the ladder, you'd probably say 4.5 feet. I guess that's a small ladder. But you'd say step ladder. You'd say 4.5 feet about, or something like that instead of the square root of 20. So, I don't know. Yeah, I'll tell you. Sure. Just ask. Otherwise, I'll write it. All right, can you do the SOHCAHTOA dance again? I need for research purposes. I'm not going to do it right now. There's no way I have to like film the thing. But funny enough, I was thinking of actually filming it in my classes. I just didn't have the camera prepped in a way to do it. Maybe next year I'll actually film it. And all that stuff, I made up the dance portion of that story. By the way, it's a very popular folk tale about King Fred and Queen Wilma, of course, King Klutz and Queen SOHCAHTOA. But the dance aspect of it is fully mine. Obviously using trig, but I own that portion. Proprietary until I film it myself. And just look for it next year for research purposes. Absolutely. Yes, I did plan on recording it. The problem was there was brunch. Remember, we were on a block period, and there was brunch time in between, so I had to step out. And I had to go over a quiz and stuff first. But basically, I wanted the camera planted beforehand without you guys knowing about it. But I didn't want it to be recording for like 15 minutes on and overheating my camera. And maybe I need to check the time, or I need to check stuff for softball, or it starts overheating after a big recording, or I run out of memory. So there were logistical purposes for actually getting the recording in. But sorry, I don't have recording for you. Just the sine, cosine, tangent stuff. You're right, for research purposes. Honestly, try the dance. Go up to the front of the room thing and make sure that you got your opposite, hypotenuse, you know, all that kind of stuff. Make sure you know your SOHCAHTOA for yourself. All right, how to square root something on a calculator. It depends on the calculator. Let me pop up mine. The majority of them, if you're talking about getting to simplify a radical, that's something you got to do on your own. That's something you're expected to be able to do on your own. If you're talking about, I gotta find out how to pop mine up. Most of them, and this calculator will be different than the ones we use in classes, and if you have to ask, I guess, in class, you can, but my hope is you've been practicing long enough. We've been using calculators long enough, at least in my class, or I've been asking you to not use your phone as a calculator or whatever, that you should be expected to know how to use it kind of on your own by the time of a test. But if push comes to shove and you absolutely have to know to get something right, I guess I'll help you out. The my graphing calculator that I have here will be kind of similar to what you do here. Normally there's a button where you square something like that, and then the function is right above it. I don't mean the next button. I mean the icon is above it right there, which means you have to access the second button. So on my calculators in my classroom, I think it's a green button that's second. This one's yellow. You hit second, and then you hit that thing, and then you can take the square root. I talked about the square root of 20 before. I think it's around 4.5. Yeah, so if it rounds to the nearest tenth, it's around 4.5, and there's the button. I want to make sure my calculators are all in that mode that gives you decimals. And yeah, that's how you do it. I hope that addresses it. Good question, either way. Hope that was helpful. Okay, let's go to the next one. Can you give a brief description of the difference of sine, cosine, and tangent and how you know which one's the right one to use? So I did answer this before a little bit. If you go and check this question right here, I'm having trouble with the sine, cosine, tangent one. What I will revisit, though, is first of all the way to spell SOHCAHTOA. Let's go to that. SOHCAHTOA. because this answers that question. Relative to the angle that you have, one of the acute angles in your right triangle, if it's this one right here, relative to this angle, here's the side opposite, here's the leg adjacent to it, and here's the hypotenuse of the right triangle. Sine uses opposite divided by hypotenuse. So, and one thing I answered in that other question, I think is the first thing that I said, is there's no one trig function that's better than the other ones. It's not, sine's better than cosine and tangent, nothing like that. Depends on the information that you have. If I don't have the adjacent leg, I'm going to use sine because I have the opposite and hypotenuse. Or, you know, when I say I have, I mean if one of them's x, you're trying to find it. Okay, if it's labeled, right? I'm going to use sine in this case. But in this case, I'm going to use cosine. That uses adjacent over hypotenuse. And in this case, I'm going to use, whoopsie, in this case I'm going to use tangent because I have opposite over adjacent. It's fine. If you have all three, it's your choice. Use the one that you think you'd most benefit from. Maybe one of them has a radical and you want to avoid it. Maybe these lengths are, and I need to do something that actually works. What was the one from our quiz? We had root 5 and 2, and you had to find out that this was 3, whatever. But let's say it was these ones. Well, maybe I don't want to use sine or tangent because I don't want to use a square root. Listen, a square root doesn't make the problem harder. Oh, this is to find an angle measure now, by the way. This is now to find an angle measure, not to find one of the sides. But, yeah, it's like, okay, I don't want to use the square root, so I don't want to use anything with opposite. So tangent's out and sine's out. I'll use cosine. I'll say the cosine of my angle is 2/3, and then I'll take the inverse cosine of both sides, and I get inverse cosine of 2/3. Now, that's no different. Whatever answer you get here is the same thing as the inverse sine of root 5 over 3, and the inverse tangent of root 5 over 2. All of these are the exact same answer. Try them in your calculator. I'll go do it right now. I need to make sure my calculator's in degrees when I do so, because it's probably not. It's in radians right now, so I got to be in degrees. But yeah, if I take the inverse cosine, I don't know what the angle is, but if I take it's probably close to 45, a little more than 45. Inverse cosine of 2/3, yeah, 48, whatever. Inverse sine of root 5 over 3, excuse me, is that number, and inverse tangent of root 5 over 2 is the same number. So, you know, they're all the same, they're all the same value, and the reason is because they're all referencing the same angle in the same triangle. It's a triangle with those ratio relationships, and that's the angle measure. So there's no one versus the other that's kind of preferred or anything like that. It's just a matter of what it is you have, what it is you're dealing with, all based on SOHCAHTOA. It's all based on SOHCAHTOA. Keep those up there in case I need to use them again. Let me just get rid of this crossed out part. So, SOHCAHTOA. So I hope that helps answer your question. How many questions do I have left? I don't know. Where am I right now? I'm here. So I have those. I don't know if this was a question. I just copied and pasted. Was this the question? Special right triangles? Let me find my... Maybe these are one question. Okay, here we go. Special right triangles. How do you better understand when to multiply or divide by the square root of 2 or the square root of 3? This is based off your special right triangle ratio relationships. So I did fill out, if you go to this question here, which this should say 30, 60, 90. I just pasted whatever was copied. If you go to this question here, I do display them a little more. But how do you know when to use one versus the other? It's based on which right triangle you're talking about. So depends on if you're talking about the 45, 45, 90 or the 30, 60, 90. The 45, 45, 90 has a root 2 in it, and the 30, 60, 90 has a root 3 in it. So this one has the root 2. I multiply by root 2 when I know the leg of my 45, 45, 90 triangle, and I'm trying to find its hypotenuse. This is a multiply by root 2 scenario. I want to multiply by root 3 when I want to multiply by root 3 when I know the short leg of my 30, 60, 90 triangle here, and I need to find the long leg of it because it's root 3 times larger than it. That's when I do which one I do. What you want to understand, not just you who asked the question, what students want to understand here is these right triangles are special because these ratio relationships are so clean. together. But any 45, 45, 90 triangle has this ratio relationship. It doesn't matter how big or small it is. Remember, a 45, 45, 90, no matter how much I grow or shrink, it maintains that ratio relationship, this 1 to 1 to root 2. And same with the 30, 60, 90. In any 30, 60, 90 triangle, the long leg is always root 3 times larger than the short leg. And I know hearing root 3 sounds weird, so let's go with the hypotenuse. Hypotenuse is always twice as long as the shortest leg in the 30, 60, 90 triangle. It doesn't matter how big or small that triangle is because of similarity. Similar triangles have proportional side lengths. And this is the proportionality of a 30, 60, 90 triangle. Anyway, that's when we multiply by the root 2 versus the root 3. It depends on which triangle you're talking about. 45, 45, 90 triangle has a root 2 in it for the hypotenuse compared to the leg length, either leg length. And the 30, 60, 90 triangle has a root 3 in it, which represents the long leg in comparison to the short leg. It's root 3 times larger. All right, the next question is, can sine, cosine, and tangent only be used for right triangles? No. But the ratio relationship, well, I don't know how to answer that for you in IM2. You can use it in other triangles, but its function served is based on a right triangle premise. Best I can say, I feel like I know who asked this question, because just based on the more enriching thing, I don't know for sure. I do have a video, well, I have many videos, but in one of my recent videos, I actually ran into a question. I'm like, this isn't an IM2 question. This is law of cosines. Let's say, that actually almost looks like a right angle right here, but let's say this was like 80 degrees and this was, I don't know, 50 degrees. Well, this was, say, 55 degrees and 45 degrees right here. Can trig be used in here? Not in the way that you'd expect. And by the way, I'm not coming up with more lengths and whatever. The bottom line is, though, if there is some sort of thing that's used in terms of sine, cosine, and tangent, because I could use, if this length was, 5, I could find this x by using something called the law of sines. There's another formula involved with it, but you know what it's entirely based on? Just ignore that 80 for a second. I don't really need the 80 for this problem. It's entirely based on the fact that an altitude can be drawn in this part right here that divvies up this into a right triangle here and a right triangle there. And therefore sine is used in some way to gather some h, which is equivalent in both of these things here. Bottom line is you can use trig in non-right triangles, but it's based off a right triangle premise even still. Even the unit circle, which is something you wouldn't know anything about it, but IM3 people will. Even the unit circle has a right triangle premise to it, even though it's a circle. There's still a basis of right triangles that build into it. So can it be only used for right triangles? In your sense of the realm, yes. Don't start using sine as opposite over hypotenuse. When I say opposite over hypotenuse for sine, even for this problem here, I'm using it specifically with that altitude. But if you get rid of this altitude, you don't start to say sine of 45 is opposite over hypotenuse like it's 5 over x. 5 is not an opposite in the way that it's from a right angle. This is not a hypotenuse. It's not a right triangle. So, unless you build the altitude. So it's not in the way that you'd think of it when we talk about it. And I don't know if that answers the question fully, but it should in a way for you and IM2 to know. And in IM3, you wouldn't ask the question because you'd understand that there are other forms that you can, yes, use it. All right, how do I know when to divide by a cosine versus multiply by a cosine? Cosine spelled differently. Let's go ahead and spell that one. So cosine. Well, cosine instead of sine or tangent, I assume you just mean trig functions. I guess what you're asking is this. Okay. I guess what you're asking is this. In what scenarios, and I'll use cosine as the example. I'll use an adjacent and hypotenuse. Let's say this is a 40-degree angle right here, and this is your unknown, and this side length is 10. And they say solve for x. To answer your question, I'm going to say you know based off of your setup, your trig setup, your trig equation, and then what you choose to do algebraically to solve for your variable. So my trig setup for this equation will be this. Relative to my 40-degree angle, I'm looking for the adjacent. I know the hypotenuse, so I'm going to use cosine. So my setup is cosine of my angle. This isn't cosine times, by the way. If this is what you're asking, I'm just going to say this is not multiplication. This is applying a function. But I don't think you're asking that. Equals adjacent over hypotenuse x over 10. So your question might be, how do I know that I multiply 10 by cosine of 40 instead of divide it with cosine of 40? Something like that. That's what I think you're asking. And my answer is you got to know your algebra-based things. X is what I'm solving for. X is being divided by 10. In order to solve for x, I got to multiply both sides by 10. That's the setup. To get x by itself, 10's got to be multiplied. So 10 is multiplying with the cosine of 40 in this case, right? Here's the exact answer for x. I'm just going to leave it like that. X is 10 times the cosine of 40. Whatever that calculates to is whatever, right? Let's flip the script on that one, though, and let's put 10 here and x here. Completely different question now, by the way. It's not like whatever was x before is x now. Cosine of 40, in this case now, equals 10 over x, adjacent over hypotenuse, but now the x is here. Technically, it takes 2 steps to solve for x, to get x by itself. The first step doesn't actually get x by itself, but in order to solve for x, you got to get it in the numerator of its own question. You got to multiply both sides by x, same way as we multiply both sides by 10. Difference is, x is not yet by itself. Now this equation says x times the cosine of 40 equals 10. And you might say, well, we're multiplying by cosine of 40 again. Well, not so fast. Now we're going to divide both sides by the cosine of 40 to get x by itself. So, in this case, x equals 10 over the cosine of 40. And whatever that answer is what it is. Now, 10 times the cosine of 40 is going to be a number less than 10. 10 divided by the cosine of 40 is going to be a number greater than 10. The reason I know that is because, in this case, x is the hypotenuse. Hypotenuse should be greater than a leg. So when you ask, and last time x was the leg and 10 was the hypotenuse. So when you ask, how do I know when to divide by cosine and multiply by cosine and things like that, part of the answer is whatever value you get in your calculator, ask yourself whether it's a red flag answer. If I end up getting an x value of 7.6, something went wrong because I should get a hypotenuse that's bigger. So you got to ask yourself, did I do the right algebra to get there? In this case, this will be bigger than 7.6. I don't know. I don't care what it's going to be. But it's going to be something bigger than 7.6. It's going to be bigger than 10, and it should be. And if it was less than 10, something went wrong. So that can help answer it as well. How do you know when? Well, you should also know the size of your numbers in comparison. And hopefully that somewhat addresses it. Okay. I don't know how many questions I have left here. I never did check. But these questions are kind of big. I don't really know how to properly structure this question, but for lesson 9.2, I was confused myself in which side to multiply, divide, as well as when the square root numbers and whole numbers are in different places in different problems. Was there more? I hope that makes sense. Thank you. Yeah, mostly what I'll say is I did answer it several times just by setting up ratio relationships. I might have even done a problem. Check out these questions here. This one, the ratios, sides of a 30, 60, 90. This one on the 45, 45, 90, 30, 60, 90. They said it wrong, but 30, 60, 90. And then this question here on how to understand when to multiply or divide by the square root of 2 or square root of 3. But once you've drawn that triangle ratio relationship, it's hard to get it wrong because, here, I'll answer it in a different way. You can still take those answers because this is going to be a different way for me to answer it. What did I just do? Remember, this is all about similarity. I'll do it with just one example, and then I'm going to cut it. So 45, 45, 90. This ratio relationship's 1 to 1 to root 2. Why? Because it is. Pythagorean theorem, isosceles right triangle, all this kind of stuff. We can get there. Now, that's just the ratio relationship. This applies to any right triangle. So when you get a right triangle as an example, when your example says a 45-degree angle here, it shows a right angle there, and it shows a length right here of, because I want to rationalize denominators. I don't know if anyone's going to ask me about it later. Length of 2. I want to get something good. 9 root 6. Actually, that's not good enough. I'll just do 9 root 7. Excuse me, let's do 8 root 7. This is what happens when I come up with something on the fly. And it says solve for the length of A. Solve for the length of A. Well, the way I would say this before is straight up as I would generally say it is root 2 is root 2 times larger than 1. So to go from root 2 to 1, you divide by root 2. So you divide this number by root 2 and you get A. But you don't have to go about it that way. What we know about similar triangles is corresponding sides are proportional. So we should know that this leg corresponds to this leg, this hypotenuse corresponds to this hypotenuse. You can make a proportion out of it. I can say something like 1 over A equals root 2 over 8 root 7. I mean, this is just another way to go about the problem. Cross multiply, all that kind of stuff. You get 8 root 7 equals A root 2. Divide both sides by root 2. But that's the ultimate thing that happens. You divide by the square root of 2. This is the square root of 2 times smaller than that guy. So once you know these ratio relationships, use them with the parts that correspond and say, I'd have to divide this by root 2 to get that number. So I have to divide this by root 2 to get that number. It's that kind of thing. Anyway, I'll just continue on the problem. A is 8 root 2, or 8 root 7 over root 2. And I got to rationalize this denominator. Multiply top and bottom by the square root of 2. And then you get 8 root 14. 8 root 14 over 2. And 8 over 2 is 4. So you get 4 root 14. And root 14 can't simplify, and that would be the value of A. I don't know. But that's, yeah, the reason why we do the 1 to something is because 1 is the smallest integer, and then I know that 1 times anything is just that number. 1 times what is root 2? Root 2. 1 times what is 2? 2. 1 times what is root 3? Root 3. So it's easy to come up with, based on that value, what do I do? Or what do I divide by to get 1? That number. Yeah. And that goes based off all the other questions before it. Where was that question? Okay, it was there. Can you please explain how to find theta? I'm so confused. What's theta? Although, sorry if I ever speak with a lisp of any sort that makes you not sure what I was saying. Theta is just a variable, but we use that variable for angle measures, so you're probably going to see it on more quizzes and tests. So how do I find theta? Theta, by the way, theta. It's a Greek letter. I answered it on the top question right here. How do you know when to use negative form of cosine, sine, and tangent? It should say inverse sine, cosine, and tangent, but that's where is it? How to find it? The idea of finding theta, an angle measure, is going to be in one of your trig-based questions when you already have certain side lengths of your triangle. So let's say I had 5 and 12 right here. I want to set up a trig function. I want to set up a trig equation the same way I would have if I knew what theta was and I was trying to find one of my side lengths. Since you didn't ask about the finding the side lengths thing, I assume you know something about that. But here's the thing. You take sine, cosine, or tangent of an angle measure, and the result is a ratio. So let's set that up. What do I do? Sine, cosine, or tangent with here? I know the opposite. I know the hypotenuse. I want to use sine. So I say the sine of my angle equals 5 over 12. Whatever angle I'm taking the sine of, I get the same as whatever 5 over 12 is. See, 5 over 12 is some random number. It really is to us. 5 divided by 12 is that crazy number. There's an angle that I can take the sine of to get that same number. I don't know what it is. Let's try the sine of 39. Let's see what that gets us. Not even close. Let's do the sine of, would it be a smaller number? 25. That was actually pretty close. So it's close to a 25-degree angle, right? That's not what I do to find it. I'm just saying that that's the idea. You're taking the sine of an angle, you get some sort of decimal value. The decimal value is equal to the ratio of the two values that we're using in our triangle. So how do you find that angle? How do you find that angle? We have to take the inverse sine of both sides. The inverse sine. That's why I wanted to point to that negative thing. Inverse sine cancels out that thing right there. So theta, the angle measure, is now going to be alone because the inverse sine of the sine of an angle is just the angle itself. So now we get theta equals the inverse sine of 5 over 12, and your calculator will find the angle measure that you got to take the sine of to get you that same 5/12 ratio, or that decimal equivalent of it. So the inverse sine, and it'll be something close, it'll be a little bit less than 25. Inverse sine of 5/12 is 24 point. That was as close as I could get, pretty much. 24.6 degrees. That's how you find it. Inverse trig functions. That's the whole point of them. So go back to your notes. Find the part where it says you take the sine of an angle to get a ratio. You take the inverse sine of of a ratio to get an angle. Or inverse cosine or inverse tangent. But it depends on which setup you have. This I would use sine, because with this angle it's the opposite in hypotenuse. Like that. Tangent would be opposite over adjacent, all that. Okay. The next question. Do you have any tips for solving 45, 45, 90, and 30, 60, 90 triangles? I find that's one of the things I struggle with most in this unit. It takes me more than an ideal amount of time to complete them. All I will say is I have answered it several times here. If you haven't tried the assignment, because I think the assignment I gave you was a worksheet. And look, it might have had a video on it, it might not have. But if you want to just see more examples of them, I would say go to the textbook version. Like, go to 9.2 in the textbook. Find my video. Find my video in my IM2 playlist of the 9.2 textbook video stuff. You'll see that I do them really quickly. If you're talking about the using the ratios, that's what I'd refer to. If you're talking about simplifying radicals, I don't know if I teach that stuff there. I just do it because I taught that back in chapter 4. I think I brought up. It's back in chapter 4. So if you're asking more about simplifying radicals, rationalizing denominators, we got to look back a little bit on that. But it's very quick. You multiply by 2 or divide by 2. You multiply by root 2 or divide by root 2. Multiply by root 3 or divide by root 3. All depending on which triangle you're in and what the buildup is. So go to the other questions that I have here. Anything else that talks about 30, 60, 90, 45, 45, 90, special right triangles. There's several questions there. And I'm actually surprised there are more questions on that. Not that I'm surprised that people don't get it. I just feel like people often have a recency bias and would only focus on the trig questions. So I'm glad people are asking it, and I hope I'm answering it pretty well. Okay, the next question is, how do we set up the ratios for solving, similar right triangles? I thought this was special right triangles again. I was going to say, and here's another question. We have a similar right triangles question. So this was out of 9.3. Yeah, it's something that, we spent one day on the notes of it. And although I only read the room in a nutshell of whoever's saying things out loud, I felt like we had a pretty good gist of it. That doesn't mean we still do, and that doesn't mean that everybody did. And that doesn't mean it's always the easiest thing unless you're hearing it from the teacher. Like, I've had many times where I'll hear something from my teacher, and I'll fully understand what they're saying when they say it. It's just that when it's time for me to do it for myself, I can kind of freeze up, right? Like, I can understand them. Doesn't mean I can do it for myself. Anyway, let's say you have a right triangle right here. The big one, right? Big right triangle right there. I now will draw an altitude to this hypotenuse, and then I construct another right triangle right there called the medium right triangle. And this guy here is the small right triangle. Clearly, that means there's also a right angle right there, right? They have their own. So there's big, medium, small. All of these triangles are similar in that they all grow proportionately with one another. I will give you letters with these things here, like that. And let's redraw them so they all face the same direction. Let's start with the big one. Here's what it's all about. Short leg, long leg, hypotenuse. Which ones are which? Where's the right angle as well? B is the right angle in the big right triangle. The short leg goes to A. The long leg goes from B to C. The hypotenuse is from A to C. Confirmed. Let's go to the medium triangle. The medium triangle's right angle is D. From D to C, this is basically drawn the same way. From D to B is the short leg. From D to C is the long leg. From B to C is the hypotenuse. The small right triangle, imagine if you could rotate it downward. The small right triangle also has the right angle of D. In this case, it has a short leg of A from D to A, and the long leg from D to B. And the hypotenuse is from A to B, like that. You asked, how do we set up the ratios? More so probably proportions. How do we set up proportions? The reason I did the redraw was to reconfigure the idea that there's a short leg, long leg, hypotenuse in the big, medium, small triangles, and that you can do this for yourself as well. So if you had information, if I knew that this was 8 and this was X and this was 20, as far as my redraws go, look at the small triangle. I know that this short leg is x from A to D. Hypotenuse is 8 right there. In the medium triangle, I only have this 20 as the long leg. And in the big triangle, I have the short leg of 8 and the hypotenuse of x plus 20. Whoops, that's not the hypotenuse. And the hypotenuse of x plus 20. Why does this help me? Because I can build a proportion with the big triangle and small triangle together. How come? Because they have corresponding parts and 2 parts known for each of them. The medium triangle not only has only one known part, but it's also a part that doesn't correspond to these guys. I have the long leg for it. I don't have the long leg for these. Whereas the small and big triangle, I have the short legs for each of them and the hypotenuses for each of them. And I can do like an 8 over x equals x plus 20 over 8, something like that. How about we do it without a redraw? It's still the same thing. You have to ask yourself, you have to tell yourself that you do have to find x, right? So you're like, okay, I have to find x, and I recognize what x represents in a part of my triangle. X represents the short leg of the small triangle. Short leg of the small triangle, right? Which means I need to also find the short leg of another triangle. Do I have one? Not for the medium, I do for the big. Therefore, I need to do something else from small to big that correspond. And hopefully this problem has enough information for it. In the small, I don't have the long leg, but I do have the hypotenuse. Do I have the hypotenuse of the big? I do if you add x and 20, yes. So I can come up with the thing there. So short of the small is x. This is the part I don't always write, but I say it out loud. The short side of the small triangle is x. The short side of the big triangle is 8. Hypotenuse of the small triangle is 8. And hypotenuse of the big triangle is x plus 20. So it's that kind of thing that I do, that I call out. Generally, you want to identify what your variable is, what parts it represents, if more than one, because it can. As you could tell, 8 represented 2 different things, the short leg of the big triangle and the hypotenuse of the small triangle. You do have to not only correspond parts, like short leg, hypotenuse, hypotenuse, but you also have to go in the same order, the same direction, small to big, small to big. So that's how you do it. That's the idea. You have 2 different forms. I recommend triangle redraw if that helps you, because it's all about triangle similarity. But that's another example of that. And I'm glad someone asked something in 9.3. Awesome. All right, I'm going to move forward. I think we have 2 more questions. What's the easiest way to remember how to solve an equation that asks one to solve for an x, and x is the shared side of 2 connected right triangles? Oh, it's another question, like it's another 9.3 question. So what's the easiest way to remember how to solve an equation that asks to solve for x, and it's the shared side of 2 connected right triangles? This was not an example of that perfectly, only because the x was not the shared side. In this case, 8 was a shared. Oh, wait, is this what you meant? I guess. X, like if this was x and this was 8 and this was 20, just flipping it around, whatever. You know, the thing that I generally do, and I just brought this up in the question before, is I first identify where x is and what it represents. And I ask myself, could I use it, or do I need to use all forms of x in this part of the problem for it? In this case, I will. But x represents the hypotenuse of the small triangle, which means I'd have to find the hypotenuse of another triangle, the medium or the big. I don't have enough information in the medium. The big is 8 plus 20, so it's 28. So I do have that. So I'm hoping I have something else with small and big to represent. With small, I have the short leg, and the big triangle, I have the short leg as well, which happens to be x again. So x represents both the hypotenuse of the small triangle, short leg of the big triangle. Neither which would correspond with each other, meaning they would never be divided with each other, or they'd never be on the same part of the fraction with each other. They'd actually be opposite each other as to cross multiply in that way if x is going to be used like that. So I don't know if that kind of addresses that, but there's an example there. The other forms that we'll have is when x is the altitude right here. Now x represents 2 different things. X is the long leg of the small triangle, and it's the short leg of the medium triangle. So in the long leg of the small, I also need the long leg of another. The medium triangle I have, and it sounds like I can use the medium again for x. So the long leg of the small over the long leg of the medium equals, now notice how x is the short leg of the medium, and I can use that, and the short leg of the small is right there, and there's another setup, like that. And then the last one that's set up, because you said shared side, so the last one that we could set up is something like this. Now x is in the big triangle as the long leg, and it's also the hypotenuse of the medium triangle. but it's the long leg of the big triangle. Do we have the long leg of another triangle? Not the small, but yes, the medium right there. So do we have something else in the big and medium to do? Hypotenuse of the big, 28, because we don't have the short side. And then hypotenuse of the medium, x. And x just so happens, remember, you don't have to use x multiple times. In this question, you do. There are some questions where x might not have to be used multiple times, and just kind of keep that in mind when it's set up. But that's how it's used. I mean, I talked about the proportion stuff a little bit more in the previous question that was asked. So maybe you can combine the two and see if you get your answer in full based on that. Okay, and I think, yeah, the final question being asked is in 9.2, I'm confused on how to get the missing side lengths from the side lengths that are already present. I hate to do this to you, but I did answer it. If you want to check out other questions, I'm going to point to them all. I'll be helpful. We can find this question. Find the timestamps in the description section. But find this question here. Anything on 30, 60, 90 or special right triangles. What are the ratios of sides? Boom. This one, I still don't fully understand the boom. The special, this is two questions in one. It's one question. They just did a line break. So this one here. I don't know how deep I go into that, but I did for multiple. 9.2, it's 9.2 right here. And this one right here. So eventually later I do a little bit more and saying I already answered it. So hopefully it's pretty in depth. Sorry that you got your question in a little late with that in mind. I guess that's what happens. That's where ChatGPT could have been better for me to consolidate these things. I would have done it more if I had like 30 questions and not just, I think, 19 that I had here. But I got this done pretty much within the hour because I'm at the 56.5-minute mark. So guys, that'll do it for this one. Thank you so much for watching Mr. Robinson's Q&A Power Hour. Again, check the description section down below if you want to find a question asked and hopefully properly answered to your benefit here. Take care. I will see you in the next one.